Hey, good morning, everybody. My name is Professor Orlovsky. I teach in the English department here, but I have many friends in the physics department. Some of them former students of mine, as a matter of fact, the best. And I've been asked to host or moderate these lectures on relativity and cosmology. This is the third lecture presented by the Center of Relativity and Cosmology here at Troy University, sponsored more or less by the Department of Physics. I'd like to issue a couple of thank yous first before we get going. First of all, I'd like to thank Professor and Dean of the College of Arts and Sciences, Govin Menon. Many of you know Govin. I'd like to thank Dr. Chris Schaefer, who's the Dean of Library Sciences. I'd also like to thank Ms. Stephanie White, who is the Social Sciences librarian, who helps set up all of this information. The title of today's talk is Threads of Reality, the Ubiquity of Quantum Entanglement and its Probabilistic Nature. The Ubiquity of Quantum Entanglement and its Probabilistic Nature, presented by Dr. Bruno Costa from the Department of Physics. Professor Costa received his Bachelor of Science and his Master of Science at the University of Sao Paulo in Brazil, and his PhD at the University of British Columbia, all in physics. His interests outside of physics and mathematics are Western classical music. In fact, if you went to the Sounds of the Seasons last December, Professor Costa was in the choir singing Messiah, and it was a really knockout show. I enjoyed it very much. And then last week, you may have seen, because he also loves the outdoors, you may have seen Professor Costa riding on a pizza box in the snow down the hill behind Rushing Hall. You know, so we had a great time. You know, in previous talks, we've heard about black holes and black matter, phenomena that are huge, massive, almost beyond comprehension, right? Well, in today's talk, we learn about the very small, quantum mechanics, the movement of particles smaller than atoms, if you can wrap your head around that. However, their study by individuals like Professor Costa reveals an influence on nature by these quantum particles as profound as the topics in our earlier lectures. Ideas, fascinating, ideas suggesting that quantum movement is faster than the speed of light. Ideas about quantum teleportation, like in Star Trek, you know. So truly, the threads of reality is as massive a topic and as complex a topic as black holes or dark matter. Let me mention that this is the third lecture. We will continue these lectures, and our fourth lecture will be by Professor Yafat Sanchez, and he's right here. Okay, mathematical relativity or relative mathematics. Mathematical relativity. Okay, thank you very much. Okay, ladies and gentlemen, let me present Dr. Bruno Costa.
So I start by saying that Einstein was wrong. Or at least it's become harder and harder to defend this position. Well, to declare it to be wrong, you need to have some metaphysical compromise, which I'm not going to discuss. But nature hasn't made it any easy to defend that God doesn't play dice. And I have the full quotation here, because he had very much quantum mechanics in mind when he declared that sentence. So what is quantum mechanics? What is the quantum theory? So as physics is an empirical science, we have to accept some facts that we just get from the world. We observe the world and you have to accept as brute facts. There can be no explanations other than that's how you observe this in the world. And one of which is that you set up your experiment, identical experiment, under identical conditions. There is no guarantee that your outcomes were going to be the same. And this can just not be true. Sometimes identical experiments produce different outcomes. Once you're faced with that, you might find that ugly or not, but once you accept that, you have to lower your expectations of what you can predict from any theory. So if you have a theory that says at 100% probability you're going to get that result, the first time you get something else, that theory is false. So the best you can expect from a theory is not a definite result, but a list of possible outcomes. You can get this, this, or that, and the corresponding probabilities. That's the best you can get. And that's exactly what quantum mechanics gives you. So it's probabilistic. So let's talk about a little bit about probabilities. It's worth taking this small detour. So I want you to think of probabilities not like a ratio between infinite many things. This is not particularly helpful. It's much more helpful to think of probabilities as an extension of logic. Traditional logic would say, oh, it's overcast today. I should go get my umbrella in my rain. So Aristotle will look at you, no, this is absurd, because every time it rains, the sky is gray, but A implies B doesn't mean that B implies A. So there is no logical conclusion for you to go fetch your umbrella. That's traditional logic, but that's not how you think. You may think, okay, my degree of confidence that it may rain increased. And that's what probabilities do for you. So probabilities, there are many ways to construct probabilities. My favorite has to be Cox's axioms. So he started by saying, well, these are reasonable expectations of our rational agent things, and that's how their minds work. And let's try to encode that into statements and obtain probabilities. So let's try to quantify how much I believe in certain statement. And that's what probabilities do for you. And once you get that, probabilities turn out to be something extremely rigid, as you may think. Rational agents have to follow some rules, otherwise they're making mistakes. And same is true with probabilities. They are rigid. You don't have much room to play with them. The rules have to do, for example, with how we compose probabilities. Well, the probability of A and B to be true has to follow certain rules. Every time you learn something, you conditional your probability. I have more information about something, then my probabilities change. So all of that has to follow certain rules. But once you have them, you can start finding things about probabilities. They become a good tool for you. And there are two tools that you get from probabilities that I want to talk about today. So these are called expected values and correlations. So let's see what they are with examples. Let's say I know nothing, which is true, I know nothing about horse racing. So someone will say, you should never bet on horses. After all, you know nothing about horse racing. Well, it's not necessarily true if the conditions of my bet are highly favorable. For example, let's say there are 50 horses. I know nothing about horses, but I know there are 50. And it costs me 2 cents to enter the competition. And if I get it right, I get $1,000. Should I enter the competition? Oh, yes, a rational agent will say yes. How does a rational agent reason to find this? Well, if it calculates an expected value. Look, I know nothing about horses, so because my ignorance is completely symmetrical, I say that every horse must have the same probability of winning. After all, I can't distinguish them. I'm completely ignorant. So I assign the probability 1/50 for every single horse, even though they look different, because I don't know nothing about them. Then I find, well, look, with the probability of 49 out of 50, I lose 2 cents. But with probability 1 in 50, I win almost $1,000. So look, this expected value is positive. It's about $20. So I should enter the competition. That's what you do. And this illustrates the point that I made earlier. So how can I improve this, my expected values? Well, first, I can make this bet even more favorable for me. Or I can learn about horses. Because if I learn about horses, then I can change these probabilities here. The horses don't come with probabilities attached to their backs. Probabilities are a property that what I know about horses, not about horses themselves. So that's how you improve these odds. So these are expected values. The other are correlators. Correlators have to do, you get different things, and you look at one of these things, and you may learn something about the other. So the classic textbook example is ice cream sales and incidence of sunburns. It's observed that if the number of hospitalizations for sunburns, they happen in the same days where ice cream sales are at high. Interesting. So if I know nothing about hospitalizations, but I happen to know the number of ice cream sales, I may change my degree of belief of how full hospitals might be, at least the dermatologist part of the hospital. So this is because things are correlated. How can things be correlated? Well, they could be completely spurious, coincidental, no particular reason. They just happen to be correlated. There could be cause and effect. But when the sprinklers are on, my lawn is wet. Cause and effect, direct cause and effect. That's one way of getting things correlated. Or they could be like the ice cream sales. There's no direct cause and effect, but there is a common cause. It's sunny. I feel like an ice cream. And I also may get sunburn. OK, so let me give an example of a correlation in quantum mechanics. And this has to do with something called angular momentum. You don't need to know anything about angular momentum, just what I'm going to say. What I'm going to say is that you can think of that as arrows, and they can point anywhere. And you know that the sum of the arrows are 0. So something like that. If arrow is pointing this way, the other arrow is pointing the other way, so that's 0. So they're always opposite to each other. And what you need to know about quantum mechanics is this very simple rule. For these particular systems, in a particular system of units, if every time you try to measure any projection of this arrow in any direction, you can only get +1 or -1, and nothing else, nothing between, not even 0. That's it. Either +1 or -1, nothing else. But you say, OK, so if I measure in this projection, so if I look at the shadow of this arrow in this direction, I can get +1 or -1. In this direction, same, +1 or -1. Oh, but what if I take this perpendicular direction? Can I get 0? No, you got it. Yes, only +1 or -1, nothing else. That's all. It's as simple as that. But you also have this joint. You know something about this pair of these things. That you saw that the sum is 0. So if you measure +1 in any angle, in any axis, you choose an axis, you measure +1. If you choose a corresponding axis here, you get -1, and vice versa, because they have to add up to 0. So that's a perfectly correlated system, or anti-correlated system, in quantum mechanics. So you might find, well, that feels uncanny, but I'm trying to convince you just temporarily, that's not so uncanny. There are correlations in classical physics too. This is my experiment. I get a big pile of dollar bills, and I cut them in half, the whole pile. I take one of the halves at random, could be either half, and I put in an envelope, and I number the 2 envelopes with the same number, and I put in an envelope, and I take the other half and I put in the other envelope with the same number. And I keep doing that. And I have a pile of envelopes. And I get one of these piles, and I ship to Andromeda. And I keep the other pile of envelopes here in Troy. Centuries later, archaeologists find my envelopes. And they start opening the envelopes. Oh, envelope 1. Oh, look, there is a pyramid. Oh, envelope 2 also has a pyramid. Oh, do you know what? I remember my friend in Andromeda said something about finding a pile of envelopes too. Let's try and compare the results. And they find surprising. Every time I find a pyramid, they find an eagle, and vice versa. We never find 2 pyramids or 2 eagles. Oh, there must be some sort of spooky action at a distance that every time I open an envelope, a signal gets sent to Andromeda to say, oh, no, that sounds ridiculous, right? Well, so that's not why Einstein called this spooky action at a distance. As you may suspect, it's something a bit more delicate than that. And now I'm trying to convince you why. So stay with me, because after that, you're going to get an insight into the most profound conceptual things in quantum mechanics there are. So let's see why they are different. I'm going to convince you that they are different. And this argument was first done by this person, John Bell. So the argument is the following. We agreed that quantum mechanics, you can only get +1 and -1, no 0. In classical physics, you could get 0, but not in quantum mechanics, +1 and -1. And let's choose not one axis, let's choose 2. Okay, let's choose 2, and let's choose the axis at random now. Let's not arrange which axis we are measuring, the projections. And let's do it for both particles. And let's list all possible scenarios. There is nothing else. So these 8 possibilities will exhaust everything. There is no other possibility hidden here, because these possibilities, so this is saying that you measure 1, +1, +1, and +1 in all 3 instances for your axis. And then the corresponding, because they have to be perfectly anti-correlated, they have to be minus, minus, minus. If it's not like that, then you find an experiment with 2 eagles or 2 pyramids. It has to be like this. And you go possibility by possibility. And that's it. That's 8. There is nothing else, because you can only measure +1 or -1. So I hope you all agree that this exhausts all possibilities. Okay? So I listed all the possibilities here. So now I'm going to find this product here. I decide why. Well, because it works. I decided to calculate this particular product here. So you take this one times this 2 plus this one times this 2. You do this. Okay? And you find the values. I did it for you, one by one. 2, 2, -2, -2, 2, 2, either 2 or -2. Okay, so I don't know how these particles were created. I don't know who programmed these particles. There might be things, but so the probabilities, I'm not saying that 8 possibilities are equally probable or anything like that. They might be a mixture. Maybe possibility 3 has 99.92% probability, and the rest, 0.08%, is distributed around these other 7 possibilities. I'm completely agnostic about that. But one thing I know, no matter the probability I choose here, if I find the expected values for this column, it will be between -2 and 2. There is no way. This can never be higher than 2, because there is no single possibility this number is higher than 2. So that's all I'm saying. So you conclude that this thing has to be bounded by 2, necessarily. So this is not exactly the version Bell wrote. This is Clausen-Horn-Shimony-Holt. That's a simplified version of it. Bell's is a little bit more general, but that's what it says. That's all it takes. Okay? You list them all, you count, and you conclude that. And now you make the same calculation in quantum mechanics. What do you get? +2 square root of 2. That's 2.83. Oh. Okay. So it doesn't work. Right? But that's exciting. That's exciting, because for the first time you can tell apart if your particles are something as weird as quantum mechanics says, or if it's just like the dollar bill experiment. Now you can distinguish that experimentally, and they did. And the results agreed with quantum mechanics. And I quote John Bell himself. He was just saying, well, how reasonable it is to expect that the photons were just pre-programmed. I might not know the results, but they carry tiny programs with that. Sometimes they say, well, I'm going to give +1. Sometimes I'm going to give -1, according to a certain program. And they are just programmed to be like that. And that's how he thought. So he could make a table, just like the dollar bill. But no, the experiments are clear. Quantum mechanics is right. And that was the 2022 Nobel Prize for Physics, by the way, for these experiments. Okay, so what went wrong? I'm going to translate all that to English, so don't worry. So what do we need to do to create those tables? Well, you just need 3 assumptions. And that's what I'm going to say what they are now. The first assumption is that, okay, so there are these things that I might not have access to. I have no idea. I'm ignorant about something, like I was ignorant about horses. So there are certain variables that if I start learning about these variables, I start improving my probabilities, just like learning about horse racing. But they are not accessible to experiments, so I'll never know. That's one assumption. The other assumption is that once I learn these properties of one particle, I cannot learn any more by knowing the properties of another particle there. So this means being local. So the combination of two, saying that local hidden variables, that's what they say. So let's know that if I have no access to these things, but if I did, I would improve my predictions. And in a way that's local. So this probability is factorized. So I don't gain anything else by learning more from the other ones. So that's one condition. And the third assumption is called status independence, which means that I'm free to choose at random which axis I choose to measure without having to. I don't have a mastermind saying that whenever the universe is such that you don't have free will, you must choose this axis at that given time or something collapses. So that's denying that. So these are the hypotheses. So you have to give up at least one of them. That's what quantum mechanics is telling us. So they are all reasonable for most people. Maybe not to Niels Bohr, but for most people, these are all natural assumptions. And nevertheless, at least one has to be incorrect. And at this point, you may feel uneasy because somehow you may feel like these particles are communicating, perhaps even faster than light. That's Einstein's phrase, spooky action at the distance. And if you were here for the first installment of this series, there was all about these light cones. Now there's someone saying that this doesn't matter if it's inside or outside the light cones. So what's happening? I'm trying to convince you that nothing is happening. Everything is compatible with relativity. Because, look, if I know the outcome of an experiment in Andromeda, I can certainly improve my predictions here. But how can I know the outcome of an experiment in Andromeda? Someone has to send me a message. They say, send me a text, and then I have to wait until the signal propagates with the speed of light, and then I look at my phone. Oh, OK, now improve the probabilities. Now improve my predictions for my own labs. But if I want to do it before my text arrives, then I have to say, look, I know that the person measured, but I don't know the outcome of the measurements. So I'm going to use the rules of probabilities and find my new prediction. So I have to consider the possibilities of all possible outcomes the person measured, that outcome, and that with that probability, the other outcome, and I improve by taking this sum, so I add all these probabilities. And what do I get? The exactly same probabilities if the person had never measured at all. So nothing changes. All my predictions are identical. So there is no communication. There's no faster than light signaling. So just to repeat, because there are certain misconceptions about the violations of Bell's inequality, so I'll have to be exceedingly clear that. There's no spooky action of a distance, because there's no Cauchy effect. There are correlations. The correlations are stronger than in classical physics, but there is no conflict with relativity. It's often said that quantum mechanics says that particles don't have properties until you measure them. I'm sorry, that doesn't help you anything. You may still think this is true, but mathematically that's the same as those conditions about probabilities, so that's not helping you. So this doesn't evade the hypothesis, so the mathematics is identical, the conclusion is identical. And finally, that there are no hidden variables. That's not true. They are no, as long as they are local. The locality is important here. OK. So at this point, you may be thinking, OK, you convinced ourselves that quantum mechanics is weird. But maybe this is a quirky feature of certain particles. But if you allow it to take one leap forward and go one step more fundamental in physics, I'm trying to convince you that this is actually not the case, that entanglement is absolutely everywhere. And that has to do with some conflicts. So even though entanglement doesn't pose a conflict with relativity, the very notion of particles that are quantum do. So the particles that are quantum are problematic with relativity, and the reason is highly intimately connected with the rules of probabilities. Probabilities have to add up to 1. They can never be negative, etc. So for reasons similar to that, if you believe in most straightforward generalization of non-relativistic quantum mechanics, you run into trouble. So you need to start talking about quantum field theory, and that's what quantum field theory, in a nutshell, is the following. Now you don't think about particles as something fundamental. You don't start with particles. Think of a pond, the surface of the pond. There is water. Water is the basic ingredient. And there are ripples. Ripples are nothing but a certain configuration of the water. And particles are the same. So there are fields that you believe in the reality of those. And they're just certain specific configurations of these fields. And you interpret these configurations of the fields as the presence of particles. So fields are just like that. It's a bunch of numbers, for example, that vary from place to place. Like the temperature on the surface of the Earth. At every point of the Earth, there are different temperatures. So this could be thought of as fields. But the difference is that these fields are quantum now. So they are probabilistic. That you can start talking about correlators between them. So you think, oh, what happens to the temperature between here and somewhere else? And you're going to start finding those correlations again. And in fact, if you do that for quantum fields, and if you know all the correlators, that's all you can know about a quantum field. So you need to know the correlation between more than two things, but if you keep doing that, that goes by the Weightman's reconstruction theorem. So you can actually know everything there is to be known about the state of a system in quantum fields if you know all the correlators. And the conclusion that, in that framework, is that entanglement is absolutely everywhere. It's just unthinkable of things not being entangled. Let's say, that's not how you construct the theory, but let's say you try to find a state that is not entangled with anything else. So you try to find that. What you find that it's completely impossible to probe it, because it cannot interact with anything else. It's like I say, well, there's a dragon in this room, but you cannot see the dragon, you can't touch the dragon, any sophisticated equipment that you can bring won't detect the presence of the dragon, but the dragon is here. Obviously, an object like that is beyond the scope of physics. Physics can't tell you anything about that. So if you want the dragon to be detectable, it has to interact with something. And the moment it does, it has to be entangled. Otherwise, nothing works. It just collapses. The theory collapses. It doesn't make any sense. So it has to be entangled. Everything has to be entangled. And the vacuum is the idea that, okay, let's take the most elementary state possible, the one that has no particle. The surface of the water is completely still. Let's take that state. That state turns out to be entangled everything it could be. There is a bit of, I'm oversimplifying things a little bit, but that's the statement of Schlieder theorem. It's not maximally entangled. It could get more entangled in one thing than the other, so not that quantitative. But in terms of what it could be entangled with, it is. And these correlations, again, don't care. Well, they are present even if you're outside of light cone, if you're here in the first lecture, so they don't care about spatial positions. Well, they exist even at faraway distances and so on. So now, as a final thing, I want to see that, well, you may think, okay, these are just descriptions. Are you imagining this wild imagination of how complex the world might seem? But now I want to convince that it has real consequences, observable consequences that you cannot avoid. And one of these consequences is so-called the Unruh effect. And they tell you very simply that particles are relative. They are just certainly not like marbles. Marbles, you see a marble, everyone sees that same marble, maybe described in different ways. But now, what I'm telling you is the following. I find the fact, let's ignore gravity for now. Let's not think about gravity. It would just complicate things. But so let's pretend there is no gravity. And so we get people like us in this room who can be considered inertial observers. So then we select the state as the vacuum. So there are no particles whatsoever. Now let's consider someone who is moving in respect to us, and not in any way. It's accelerated, moving in a uniformly acceleration in respect to us. And this person is going to try to probe the same thing, the same room where we are at, okay? The identical system. This person will see particles, and a bunch of them. So let me repeat. I might have my detector. My detector, if you have a Geiger counter, that's what it does. You found a particle, it goes click. So our detectors won't click because there are no particles. It's a vacuum. But someone carrying this detector will start clicking all the time because they see particles. So particle is not absolute. It depends on who you are and how you're observing it. Now you may think, well, hold on, there is a problem. Okay, so how do you explain that the detector, the person carrying the detector is clicking? Certainly they explain very easily. After all, there are particles, so their detector is just detecting these particles they see. But I don't see any particles, so what are they detecting? Well, I explain. So if the detector works, it has to interact with the thing. And if it has to interact with the thing, it can also emit particles. So I say that the detector is clicking, not because it is detecting anything, but because it is emitting particles. So it was the vacuum. Now it's no longer the vacuum because there is this bloody detector detecting particles every time. So it's making noise and it's creating particles, and that's why it's clicking. So let me repeat. I tell completely different stories. In one story, there is a bath, and it's actually a thermal bath. It even say exactly how these particles behave, how many you find, and all of that. It has to do with acceleration. So that person tells this story and explains the clicks. I tell a completely different story and I describe the same clicks. If I calculate the excitation rate, how many clicks per second, I get the same number if I tell one story or the other story. Physics is not about stories. And I told that to my General 1 physics students last semester. There are witnesses in this room in a different context. Physics is not about stories. Physics is about observables and predictions and measurements that are sharp. And if people had taken this seriously, a lot of confusion in the early days of the quantum theories would have been avoided. And I want to finish with a quote by John Wheeler, and I think you understand exactly what he means. He says that I think of my lifetime as divided in 3 periods. In the first, I was in agreement with the idea that everything is particles. I call my second period, everything is fields, for reasons you know very well. Now I'm in the grip of a new vision that everything is information, probabilities, and what you can learn from them. With that, I thank you for your attention.
Okay, we have some time before many of you have to head to your next classes, including me. Dr. Costa will entertain questions or observations from the floor. I'd like to start. Now, the particles that you mentioned, do they exist as individual particles or as this strange thing you physicists have come up with, the waves? Is it a wave or a particle?
Good. So I think that this is one of the questions that. So the distinction. So this has to do with the early days of quantum theory, in which there were this phenomena that were better described in terms of waves or particles. But I think in the language of quantum field theory, they are neither. They are really just. You should be really thinking about fields, and that's it. And that's it. And now, if you try to describe that certain phenomena, they're more adequate to be thought of as particles, like marbles, and others, like waves. They are not localized. Funny enough, so the particle colliders that you see in CERN, for example, those are the farthest as possible as being marbles, because marbles are localizable. Those aren't. They need to know the momentum, in other words, so they need to know where a property that won't allow you to localize the particles.
So a particle can never, a particle can never be pinpointed to a certain point because it exists at all, it probably exists at all points at the same time. You can never identify a particle stop in time.
If you want, not if you want to know something like you need, what the type of things you need to know to create an experiment like CERN, then you cannot. But in principle, I wouldn't say so. In principle, you could have something that you would know where it is. But the point is that you should think of that as just a particular configuration of something that really is there and it's absolute. So the description like this is observer dependent. Yeah. Someone see particles and I may not see a particle, but the water isn't. The water is absolute. But just the configuration it turns out to be observer dependent.
It's maddening.
At the beginning, I don't want to commandeer the conversation, but at the beginning I mentioned something in what I was reading about quantum teleportation. Because if the spin of the particle is like horizontal over here, there's a minus particle spinning over there. So is it theoretically possible that we could sometime identify like the negative spin of the particle over on this side and combine the two?
Yeah, you can combine. What you call teleportation, it's more than that. So you start with a particle of the same type in your lab, and because particles are very simple, so you don't need to know many properties of the particles until you have something that is absolutely indistinguishable from the first particle you started from. So if you communicate the state of a particle and you perform an operation, and you can get an identical, you destroy the state of the particle that was in another lab, and you create a particle in your lab which has all the properties that you started from before. So it's the same particle. So in that sense, you teleported the thing without actually having a flux of energy going with you from one point, from one lab to the other lab. So that's what it is.
You seem to have denied that the quantum movement can be faster than light?
That's correct, yes. I will have no reservations and say that this is impossible, yes.
Oh, sure.
The correlations are there, but they might be just spurious correlations. No, they're not spurious, but it's not causation. It's not causation.
That takes the fun out of it. Other observations?
Ava, go ahead.
I just have a quick question. I wasn't able to come to the first couple of meetings we were doing, but just for knowing sake, how do you define a particle? What is a particle we're talking about? Is it like energy? Is it part of an atom? What are we?
I love your question because it shows how unimportant the definition of a particle is. I mean it seriously. It becomes important when, in certain conditions, like the room, we can talk about particles very, very easily. But in general, it's not even guaranteed that there is a definition of a particle. And in fact, if you turn gravity on and you have something that if you have gravity and you have things moving in time, so you have things that are fluctuating, you cannot define particles. It's not something there's just nothing. There's nothing there's no candidate for talking about particles. But there are fields. The fields are there. All you need to know is the field. And you can make all the predictions, all the experiments, using fields alone. You predict everything. The stories, and then the particles is more about the stories. It's not about the predictions. It's not about the observations. It's not about what actually the theory says it is out there.
And then the fields, were we just kind of saying that was like a whole mass of particles working?
No, they are the fundamental entity. So you're thinking of water as being made of particles. Now forget that. So let's go before the atomic theory. Let's say that the fundamental thing is just the water, this massive thing, and if there are ripples, okay, you may describe those ripples as particles. But you don't need to. If you want to predict any experimental outcome of any experiment that has to do with the water, you can do it, and you can get away just by describing the water itself. That's what I'm trying to encourage you to think of.
And then maybe this will, my next part of this question is, you had the one slide with the 8 possible outcomes
Yes.
of the 3. What are the 3 supposed to be?
Yeah, because you have 3 axes, so you could choose axes at random, right? So there are 4 different things here, but you set B2 equals A1. That's part of Bell's ingenuity. He found that if you find this particular combination, you can find a quantitative difference. So if you take other combinations, there is no guarantee that this thing is going to lie outside of the predictions of this thing. So these are all possible outcomes. So this first axis, first particle, second axis, first particle, first particle, second particle, first axis, and so on.
And
let me offer a small wrinkle in this. This is, I'm more of a pure gravity person, not particles, but nonetheless, when Dr. Costa says, don't worry about particles, it's the fields that are there, perhaps what he means is it's the fields that are not there. Because these fields may not be physical, like a Dirac field may not be realized in, there's no such thing as a field. When Dr. Costa means a field, he means a mathematical object, perhaps. But if you have new information, then I could stand corrected. The Dirac field, for example, cannot be measured. It's not.
Oh yeah. I'm not saying that it can be measured. Yeah, right. Yes, they can't be measured. Well, right. I'm trying not to take a metaphysical position and say that the physics, what the theory says, the basic ingredient says. I'm not trying to ascribe reality to that, because that's again going against my premise that physics is not about stories. But so there are these entities that they are in the theory, but there are rules of what you can measure given that these entities are there. So it might be might not be the field itself, but you can perform experiments that have to do interactions, and from those interactions you
also offer this. If you have to somehow try to describe a particle, this is a difficult task, but somehow if you have to identify of what a particle might be. And did you say you're an English major? You will like this answer, mostly because it is the version that's closest to being plausible. A particle is a realization of a symmetry that the universe possesses.
So are you saying, like, with the arrows, with the one direction going this way and one going that way, one has to have another, is what we're saying?
The mere existence of a particle is, the universe has certain symmetry properties. Now, what do I mean by symmetry? Symmetry is something that does not change while you make a movement in a certain way. There's that symmetry that is not violated. Something remains true. And the essence of what remains true is what we might call a particle. Dr. Costa, I know that's that's a little bit of a stretch, but what I'm trying to explain here is that particles are perhaps representations of the Lorentz group, which is a symmetry.
I still don't like that, but we can talk about that later.
Or I've turned gravitation off, but okay. Right. So.
And then I'm sorry if I'm getting a little too into the specifics of the PowerPoint, but what was the importance of the quantum mechanics predicts 2.83 over everything being equal to or under 2?
Because it's not.
Yeah.
2.83 is outside of this thing.
So what does that disprove again?
It tells you at this point, you have to go to experiments. But at this point, it says that there is an experiment that can distinguish between this type of correlations and these type of correlations. These type of correlations will give you, for one particular experiment, we'll give you 2.8. Okay. This type of experiments, for the same situation, you can never get up past 2. And then you can go to the experiments and see which one is correct. And quantum mechanics is correct. So that's the most, conceptually speaking, I think this is the most profound insight in quantum mechanics there is. And so much so that there are people who spend their careers, philosophers of physics spend their careers, try to create what Bell called beable. So they try to create elements of reality. So they try to describe, okay, what are the elements of reality that create these so peculiar observation that it's not like that. So you don't want to deny any of these properties, and you're forced to, because your experiments are saying that it's impossible. So this is exciting.
So are you saying in
have to deny one of those, or generally you have to deny one of those?
I'm saying that nature nature can't have it all.
Okay, so which one is denied?
That's good, because that's open to interpretation. So there are different interpretations of quantum mechanics so they tell different stories about the world, but they give you the same predictions. So for example, when I mentioned this thing, pilot waves are one particular interpretation. So according to this interpretation, there's a particle and there's a wave. This is non-relativistic, so there are no quantum fields here. This hasn't been done for relativistic physics. But in pre-relativistic physics, you could talk about particles. And someone who defends this position will say, well, there are two elements of reality. There is a particle and there is a wave. And these are highly non-local. So there are things influence each other away from, and so all of that I said is compatible with relativity. It wouldn't be compatible with these things. But these things are measurable. So it's open to interpretation. Some people would even claim that even this thing, superdeterminism, is incorrect. Not many. But even some people would try to defend superdeterminism. Not many. Most people would just say, there are no such a thing as lambda. So there's no these local hidden variables just don't exist. And that's closest to the fathers of quantum mechanics were trying to say. But they were also influenced by the school of thought of that time, which was the Vienna Circle. So there were logical positivism everywhere. And they were trying to say, well, you can only talk about things that you can detect. Otherwise, certain sentences are just meaningless. And so they were influenced by that. So Niels Bohr, anyway. So, but this is open to interpretation.
So it depends on how you look at it, what you think, and what the numbers.
The numbers, yes, exactly. So any interpretation that you choose, you may interpret quantum mechanics in very different ways, but at least you can't have all three for your interpretation. So I don't think it's possible to decide empirically which one is correct. With small exceptions, leaving some small exceptions aside, it's empirically indistinguishable. So I can give you an answer for that.
Dr. Costa, will artificial intelligence crack the mystery?
Which mystery? Entanglement?
The mystery of, what is a particle, and what's it doing here? And
yeah, I think.
What's the advantages of
I think there are certain concepts that are useful until they aren't anymore. And I think this is just one of them. For particles, it started being very useful in a certain time in history. And physics developed a lot because of that. But once you start learning more about things, and you see that they are just limited. And sometimes we just shouldn't be talking about particles. And it's not too different. That's happened in the history of physics over time and again. So I think that's why I insist about not being about stories. Because if you cling to stories, you have to change it. You have to change them.
Okay, let's give Dr. Costa. Oh, one more. Sorry, yes, one more question. Go ahead.
So, in the quantum mechanics, can an observer then alter reality, or reality is probabilistically and is dependent on the observer?
According to one of these interpretations, you can alter. Well, you are altering reality. But the only point that I'm making is that even if you believe that, this will not evade this hypothesis. So you need something else. So even if you believe that. So according to textbook interpretations of quantum mechanics, that's what you do. But this is open to interpretation. That's related to the previous question.
Okay, let's give Dr. Costa a hand.